So welcome back to the afternoon session. We'll start with a talk by C. Seshadhri, also known as Sesh, and he'll talk about partition oracles for minor closed families.
Thank you. Take this off. Thank you very much. So before I begin, there are two major milestones that this talk represents. So first is, this is my first in-person talk since COVID began. So thank you to the organizers for that. Secondly, and rather strangely, this is the first time I've been to MIT in my life. So again, thank you to the organizers for that. So, okay, let's go ahead and begin. Again, before I start, tribute to my teachers. These are people who have really influenced my life and because of whom I think I'm here. Manindra Agarwal, Bernard Chazelle, Mike Sachs, Tammy Colden, Ali Pinar. This work is with my co-authors, Akash Kumar, who's currently at EPFL, and Andrew Stolman, my student, who's finished in at Katana Graph now. Okay, so we all know and love planar graphs, rich algorithmic theory, and this talk is a lot about understanding algorithms on planar graphs. One of the things that we love about planar graphs is the Lipton-Tarjan separator theorem. So planar graphs have root n size balanced vertex separators. So that's this set of size root n, which if you remove, you get pieces, connected components, which are no larger than 2/3. So this is a great tool for divide and conquer. This theorem about root n size separators also holds for any minor closed family by Alon, Seymour, and Thomas. Although we don't have as efficient an algorithm, we only have, I think, maybe the best near linear algorithms. What is even more interesting is if you take this idea further, if one looks at bounded degree planar graphs, they are hyperfinite. So this is sort of buried in a lot of existing work, but I think Elek is the first person to have sort of explicitly called this out and noticed it. You can remove a constant fraction of the edges to get connected components of constant size. So specifically, you can remove an epsilon fraction of the edges. So I'm measuring edges as n times d, where d is the degree bound. Think of the degree bound as some constant. So you can remove an epsilon fraction of the edges, and you can get connected components of size 1 over epsilon squared, constant sized. And you might ask, is this tight? And indeed is the case. By the way, to prove the hyperfiniteness, you can just recursively apply the Lipton-Tarjan separator theorem, and then it's a good exercise in divide and conquer and working out recurrences. Consider the root n cross root n grid. This is a graph with n vertices, a planar graph. And if you wanted to divide it up into small parts, you'd kind of do the obvious, right? You'd cut along lines, and you kind of separate them out equally. And if you wanted to remove an epsilon fraction of the vertices, you would cut an epsilon fraction of the lines equally spaced. And so you would cut epsilon root n lines. And then what happens is that the width and the height of each region, the perimeter of each region becomes 1 over epsilon. And so the area is 1 over epsilon squared, and you get connected components of size 1 over epsilon squared. So this epsilon to the -2 is optimal. Now, hyperfiniteness is an extremely powerful tool for approximation algorithms, because suppose you have access to this decomposition, and you wanted to estimate maybe the max cut. So what you could do is, and again, this, I think Newman Solar is the first people to explicitly call this out, is you could pick a constant pieces at random. You could apply the exact algorithm on those pieces and scale the answer. So if you wanted max cut, you could do this. If you wanted the min vertex cover, you could do this. If you wanted the matching, you could do this. Indeed, you can do this for a very rich collection of problems if you have access to this hyperfinite decomposition. Right, so by the way, any questions, please feel free to interrupt me, although Elena is going to have to then take the mic. So, okay, so this is hyperfiniteness leads to a powerful tool for approximation algorithms. And so that's why, I have this nice hammer. I believe this is what I found when I searched for Thor's hammer on Google. So suppose you have access to this decomposition. As I said, what it leads to is constant time. By constant, I mean it's some function of epsilon and the degree bound d, which we're treating as constant. And you get additive epsilon n approximations for a variety of problems. Essentially, any problem that sort of Lipschitz with respect to edges, meaning that each edge can only change the objective by a constant. So for any such, and with certain extra conditions, so like vertex cover, max matching, independent set, dominating set, distance to any additive monotone property, a whole list of quantities can be approximated. Essentially, it says that you can treat your graph as a collection of small connected components, and small being constant. In this case, it's 1 over epsilon squared. Now, I said you can construct this decomposition in linear time, but then that would completely sort of, obviate, so then, why would you want constant time approximation algorithms on top of that if you're spending linear time? So what we would like is access to this decomposition, but we want local access to this decomposition. And I'll explain that formally shortly, but you can kind of interpret what this means. It means that given any vertex, you want to know which piece it lies in. Find the connected component of the hyperfinite decomposition. And the paper that sort of introduced this, Hasidim, Kellner, Huiwen, and Onak in 2009, this was a beautiful paper that, it's a seminal paper that introduced this idea that you could actually get local access to a hyperfinite decomposition, and they called it the partition oracle. So what you want is, given a vertex V, the algorithm needs to output the component that V belongs in, and it must give consistent access. That is, if you ask it for this vertex V and this vertex U, you have to get the same component. But it's a local algorithm, right? It's only allowed to spend a constant time. And there's no pre-processing on the graph. So now let's get into some formalism. The query model I'm looking at is the classic Goldreich-Rahn adjacency list model. So the way to think of it is you have random access to the adjacency list. I also like to think of it as you basically have sort of 2 operations, right? You can select a uniform random vertex, and then you can crawl from that vertex. So you can also look up edges, which is kind of implicit in the fact that the degree bound is constant. So just think of you have access to the graph, like you can pick a random vertex, you can crawl from the vertex, you can look up edges. A partition oracle is a procedure so we have access to the planar graph as described, random access to the adjacency list. We'll have an input parameter epsilon, which is again this hyperfiniteness parameter. So on query V, we want to output a component CV. So component, think of it as a connected component of the graph. It's a connected subgraph containing V. There is going to be a fixed random seed of length n. There's no pre-processing. So all the coordination is happening through that randomness, through access to the random seed. The first property we want is what I'll call consistency. If U is in V's component, then the component of U has to be the component of V. That's just saying that the total output needs to be a partition, right? So once you fix the seed, this property must hold, that the output basically represents a partition. You want a size bound that the component should actually be O of 1 over epsilon squared. It's a very stringent component. So I want this to exactly match the optimal result that I showed on the grid. Indeed, if you get any function of epsilon, you can reduce it to O of 1 over epsilon squared with some runtime overhead, right? So you can get any sort of polynomial here, it's still fine, right? Any function of epsilon. Both these properties should actually hold with probability 1 over the randomness. Finally, we have a cut bound, which is the number of edges across these components should be at most epsilon ND. And this is with high probability over the randomness. Okay, so this is what a partition oracle is. Any questions? Yeah.
Quick question, I can repeat it. Can the random seed be n log n? So can I get a random permutation of the vertices?
Actually, probably it's n log n it's n log n, yeah. It's n log n.
Is the random seed given to all the vertices or the algorithm, or is it just that each vertex goes from piece of the random?
So yeah, I'll repeat the question. So first is this n or n log n? And the second question is, do all the vertices see all the randomness, or do they get a part of the randomness? The way the model is set up, so firstly that I should say this, the length should be n log n, so you can get a permutation. Although I think digging in, you can probably get O of n as well. Secondly, the random seed is accessible to all vertices. Although naturally, because the runtime is going to be constant, each vertex will only look at a constant portion of the seed. But it is hard to determine that a priori. There's a question regarding that I will come to at the end of the talk as to how to shorten that randomness. Okay, so the big question here is, what is the running time per query? You can even ask what is the query complexity per query, but I actually want a runtime bound. Okay, so this is the problem that we're looking at. This is a partition oracle. And so the initial paper of HKNO gave a 2 to the d over epsilon bound. Then Levy and Ron in 2015 gave a quasi-polynomial in d over epsilon. It was a very clever analysis of the original algorithm. And these are based on combinatorial methods. And the natural question is, can we get polynomial in d over epsilon? Which is like the, think of it as polynomial in 1 over epsilon. And this work is yes, for any minor closed family, there exists a partition oracle where the queries run in polynomial in d over epsilon. This polynomial is actually fixed independent of the family. So it's a fixed constant like 3,000, okay, or 3 million maybe, but they're all constants. Naturally, this gives like a host of algorithms for many different things. I won't read all of it, but essentially there are applications to many approximation algorithms for minor closed families. Just to give you some context, I'm going to flash these next 2 slides really quickly. You can ask me more if you want. A lot of these results emerged from the quest of property testers for planarity. That's sort of where this work started, and that's where a lot of this work sort of lay in that area. Specifically, this result is on a recent program on combining tools from spectral graph theory, graph minors, and sublinear algorithms. And this is like the next result on that in that journey. My title has this thing about how to coordinate diffusions. And I want to sort of explain that the main thing that happens in this result is a way in which diffusions are coordinated. And I hope to show you that because I think there are other applications, and maybe some of you can tell me other places that can use this. But before I get there, I want to tell you what is the combinatorial approach. And that way, I think we'll get a better appreciation of what is it that diffusion can do that the combinatorial approaches cannot. So the combinatorial approach for partition oracles, I'm greatly simplifying, is consider the following process. Take half the edges at random and contract them. Right? And we're doing graph minors, so it seems that contraction is something natural to do. And then rinse and repeat. Take half the edges, contract, half the edges, contract, until you end up with some graph which is of constant size. So this is a constant size graph, which I'm blowing up over here. Each vertex here is actually going to be some kind of component. It's a connected component if you blow it back. Now, it turns out that if you do this the right way, you do the math, this will actually be a hyperfinite decomposition. And you can then, to get a local algorithm, you have to reverse the contractions to get the cluster. This is obviously easier said than done, but you can do it using some clever analysis. And so if you want to say, here's some vertex, which component do I lie in? You kind of try to go here and you try to sort of reverse the contractions, and then you'll get the component. And I'm oversimplifying things, but that's the basic idea. Now, if you look at it, each step you go, there's a constant factor reduction in the edges. So there are, there's sort of many levels of recursion that need to be done. Now, okay, I'm again sort of greatly oversimplifying, but if you kind of look at how many levels of recursion you need to unpack to get from a vertex to the cluster it belongs to, with a lot of hard work, you can get it down to like log 1 over epsilon. But this means you need to look at a recursion tree of depth log 1 over epsilon. My point is, if you do this unpacking process, it's very hard to get a recursion depth which is a constant. Indeed, I don't think it's possible. And that's what you would need to do if you wanted a truly polynomial in d over epsilon algorithm. And this leads to like a d over epsilon to the log d over epsilon. Okay, I say we cannot reduce, as in we don't know how to reduce. It seems really hard. And so the combinatorial approaches kind of get stuck here because what they're effectively doing is they're looking at some neighborhood. And they're completely expanding out the neighborhood to understand what happens. That neighborhood must have a radius that depends on epsilon, because the pieces that you get are going to have size 1 over epsilon squared. Now, you can do a lot of cleverness and get the recursion down, but it doesn't seem like you can do constant. And so the idea that we had here, and because of previous successes of spectral graph theory, was to look at this somewhat differently, just look at the power of diffusions in this process. Okay, so what is a diffusion? Well, you could look at PSL. So S is a vertex, L is a length. Think of length being like some polynomial in 1 over epsilon. PSL is the distribution of the L length random walk from S. So you can think of the random walk view, which is like a particle that's moving around. I want to think of it more from this diffusion view where you think of ink dropped on the vertex and then the ink spreads. Right? And that's PSL vector is like the ink vector. And this is really like, m to the L ES, where m is the adjacency, is the random walk matrix, ES is like the indicator vector for the starting vertex. Assume that you can compute PSL exactly. Or technically you might say, well, I have to sample that, but believe me that with some approximations, you can compute it exactly. So starting from a vertex, if you do an L length walk where L is 1 over epsilon, let's assume we know exactly where it's going to lie. So we get this diffusion vector. If you look at the 2 norm squared, or just the 2 norm, this is some measure of how much it's spreading, right? So if you want to distinguish between very little spread and a lot of spread, you can look at this 2 norm squared. The smaller it is, the more it spreads. As a rough approximation, it reaches roughly 1 over the 2 norm squared vertices. So, smaller PSL squared, the norm squared means more spread. In an expander, the spread will decay exponentially in the length, right? Because if you do L steps, you'll reach like 2 to the L vertices. Now, if you go and do the math for a hyperfinite graph, if you take the hyperfinite decomposition, you can kind of believe that your diffusion will probably get trapped in your piece. You have to work through the math a bit. It's just some like Markov and some calculations, but we can show that for at least a 1 minus epsilon fraction of the edges. So for almost all the vertices, the 2 norm squared is at least polynomial in 1 over L. So the decay is only polynomial, not like exponential and expander. Indeed, you could get like 1 over L squared, if you do the math carefully. This is the only place where minor freeness is actually used in this entire result, in getting here. So indeed, even if you didn't have minor freeness, if you just had some sort of polynomial hyperfiniteness, this result will work. So for example, a 3-dimensional grid is also polynomially hyperfinite, right? Except that you would get 1 over epsilon cubed size pieces. And so now with this, so what we know is in some sense that maybe random walks can pull out the clusters from a hyperfinite decomposition efficiently. So now if you go through your normal spectral graph theory notes, or if you look at in general the Cheeger inequality, what you'll see is that when a diffusion is trapped, there's a low conductance cut somewhere. And what is low conductance? Conductance, let's just say, is the number of edges that are cut divided by d times the number of vertices, the total number of edges. So what you can show is that if this 2 norm squared is greater than 1 over polynomial in L, then there exists some set S such that the conductance of the set is really small. Again, ignore what these are if you haven't seen this square root dependence before. Just think of this as you have some set whose conductance is polynomial in epsilon, very small. And moreover, the size of this set is going to be polynomial in this length. You can do much better than this polynomials, but again, I just want to say that all of this is polynomial in 1 over epsilon, when epsilon is the parameter you're interested in. And you go, how can you find this set? And also this set kind of lies somewhere around this vertex. So how do you find this set? And this is where now we stand on the shoulders of giants. And Spielman and Tang in 2003 gave a local algorithm to compute such a set in linear time, or like near linear time. So again, what you have is you have a vertex such that that 2 norm squared is at least 1 over polynomial in the length. And the basic idea is to do what's called a sweep cut procedure. So take an L length random walk. So let's say this is non-scripted L. So for any length in between, you do that random walk, you look at the distribution that you get, sort the distribution, and then you consider what are called sweep cuts. You basically look at all the vertices that you reach with sufficiently high probability, that's a cut. You check out, is that cut a low conductance cut? You do this a bunch of times and you will find a low conductance cut. The analysis is not easy, but what this says is, so within your diffusion, you can find this low conductance cut efficiently. The upshot for us as a local, thinking of local algorithms is for a 1 minus epsilon n vertices S. So for an overwhelming majority of vertices, in time polynomial in 1 over epsilon, we can compute a low conductance cut around that vertex. So it looks like we can pick out a piece of the hyperfinite decomposition just by diffusing around it, as opposed to thinking globally in terms of contractions. Okay, this makes sense? No, it is basically about low conductance cuts around the vertex when diffusions are trapped. So it says that when diffusions are trapped, then you can find a cut with certain parameters, and I'm sort of plugging those parameters in here. Yeah, the question was does the Spielman-Tang result talk about hyperfiniteness specifically? No. It's just relating diffusion, sort of the norm of this vector to the conductance of the cut that you get. But now if you think about it a bit, there's a coordination problem here. So on the right side, I'm showing you the global combinatorial algorithm. The coordination is obvious. Okay, so maybe I'll talk about the left side. So you can find these clusters efficiently, but they won't globally give you a hyperfinite partition. Because even if you think about the grid, if you take two vertices that are adjacent, their clusters will overlap heavily, but they won't be identical. So you cannot afford to run this algorithm from every vertex. You'll get a low conductance cut from almost all vertices, but it doesn't give you a globally consistent decomposition. On the other hand, with the global algorithm over here, the one that did contractions, the coordination was obvious, like the clusters were well-defined. The issue was the runtime. And so the question is, can we get some kind of coordination for this local diffusion procedure? Sort of halfway through my time, finally I'm getting to the main point of my talk. Hopefully you're all still awake. And so how do we coordinate these diffusions? So I'm just going to read this quote by Giancarlo Roda. We mathematicians are in the habit of systematically erasing our footsteps. Scientists have looked askance at this strange habit of mathematicians. It means if you read the paper, read our paper, at some point, like, okay, how the hell did you get here? Like, what did you, like, where did this come from? And of course, we've completely hidden all of that from you. Like all the 2 years of like blood and sweat that we spent in the wrong approaches, we've hidden from you. And that's sort of what I want to show you here, because maybe it'll sort of motivate how to use these techniques, in better. So the big challenge is like, how do you decide which diffusions to pick, right? If you look at these two diffusions, they capture some intersection. Who's the one who should actually get that? Like which of these diffusions should get that portion, or which of these should actually be run? And if you look at the literature in sublinear algorithms, you might think, well, you order the seeds randomly and then you kind of start there, and then you have to bound the number of cut edges. Okay, so let me give you sort of a toy procedure, which is a global algorithm to partition the graph. Suppose at some stage, let's say we're processing vertices in order. So the vertex ID, I'm going to think of time, and that can be randomly chosen. So vertex 1, 2, 3, 4. And up to some point S, let's say there's some portion of the graph that has already been clustered. I don't know how, it's been done. And there's some set in yellow. I mean, okay, all of these colors look yellow, but to me, this looks more yellow than the others. The lightest yellow is what I'll call the free set. These are the set of vertices that have not been clustered so far. So have not been partitioned, we still have to construct our hyperfinite partition. The rest of it has sort of been partitioned through some mechanism. And this is this vertex S. So what we could do the following, we could just run Spielman-Tang from this vertex. And we'll get some, so we run some diffusion locally. So this is completely unaware of what the free set is, right? It's an oblivious algorithm that's just going to do a diffusion, and it's going to get some low conductance cut CS. Now this low conductance cut is not going to be contained in this free portion. It's just going to lie somewhere in this graph. So let's just say that the next piece is going to be the portion of the cluster so the portion of the low conductance cut inside the vertices that have not been clustered thus far. CS intersection FS. Free set intersect the cluster. This is my next piece. And then all of these pieces are going to give me a hyperfinite decomposition. Or it's going to give me a decomposition, whether it's hyperfinite or not, I don't know. And then I can just update the free set. So this is a global algorithm. But note that locally what is being done is just like some diffusion that is oblivious to the graph itself. Now, S might actually already be clustered because this is just, I've just randomly ordered the vertices and I'm running this process. This piece might be something tiny. It might even be empty, right? But the benefit of defining, so is this clear? So this is going to generate some partition of the vertices. The benefit of this is I'll show you that this can be locally implemented very easily. Okay. So why can this be locally implemented? Well, you look at any vertex S, and let's say the anchor, any vertex V, V. And let's say the anchor of V is S when V is in the piece that came when you ran S. Okay, Okay, so it's a bit mouthful. So any vertex in this red portion, its anchor is S. The anchor might lie outside, it might lie somewhere else, but that is the anchor. Now, all the vertices that got the same anchor are basically, they're basically like comrades in arms in that piece. And so the local implementation of the partition oracle is equivalent to finding the anchor for a vertex. So every vertex, if it knows its anchor, it can just do a BFS around it and find everybody who has the same anchor. That is its piece. And so the partition oracle is equivalent to locally determining the anchor. And all the potential anchors lie within a diffusion of V, because the diffusions are symmetric. If you had clustered V starting from, if you clustered this vertex V starting from S, then if you diffuse from V, you will also reach S. So the algorithm then is actually quite simple. What you do is you basically run a diffusion, and for every vertex in that blue region, compute the Spielmann-Tenk cut. And if the Spielmann-Tenk cut contains that vertex, then you look at the minimum, basically the minimum ID amongst those, and that will be the anchor. So it's like the first vertex that captured me is the one that anchors me. So the local computation is easy and efficient. Okay, but where's the catch? So that's it. Like, why am I not done here with the partition oracle? I've given you a way in which I can partition all the vertices into pieces that are actually of small size. Exactly. So I haven't bounded the number of cut edges. I've cheated because what I've argued is that this green set is a low conductance cut, but the red set might not be. And that's exactly the problem, which is the conductance of CS, which is the green part, is really small, but the conductance of the red set might be really large. This seems actually like when we were studying, it seems hopeless. Because if you look at the ordering of the vertices, it is completely oblivious to anything. And the diffusions are oblivious to the set. So how on earth are we going to actually bound the conductance of that small red portion? Because if you also think about it, at some point, this free set is going to be something like theta of epsilon. Maybe it'll be like 100 epsilon. And you still have to partition the vertices there. And so many of your seeds are going to lie, you're going to start your diffusions from outside. And you might be picking out small little chunks from here. And so the issue seems to be like we need to do some kind of amortization, which is, so here's some CS. Now look at that maybe CS, the green portion is a low conductance cut, but that red has high conductance. Now you could imagine that every 1/epsilon steps, that vertex that you chose randomly is going to lie bang inside the free set. And then at that point, you might be lucky and you'll do well, where the piece, the green and the red will basically be the same. That is, the low conductance cut that you get from Spielmann-Tenk will probably contain a lot of this yellow region, but only 1/epsilon steps. And for all the other steps, your seeds are going to lie outside and they're going to do all this like bad stuff here. So I think of it as like there's one good seed for every 1/epsilon bad seeds. And the sizes of all of these could be very different because we're basically running this spectral clustering black box. We don't know exactly what's going on. And one large bad piece could completely destroy all the good effects of your other pieces. So at this stage, sometimes you end up at the stage where you get extremely despondent, right? And then you're like, okay, I'm just going to give up. And then at some point you swing to wishful thinking. Let me just imagine the best possible scenario. Can I get this idea to work under some extremely magical situation? Suppose all the cuts had exactly k edges, right? In this case, k is equal to 3, right? So I've carefully designed this so that all the cuts have exactly 3 edges. So suppose that every time you're running this diffusion, and magically you only got a cut with k. So after 1/epsilon iterations, we'll see one good seed, which lies bang in the middle. And this cut also will cut 3 edges. But because it's a low conductance cut, there are lots of vertices in here. So if you just do the wishful thinking math, suppose the total number of edges cut in these 1/epsilon iterations will be like k/epsilon, like 3 edges for each and then 1/epsilon times. How many vertices have you clustered at the end of this? Well, you've clustered all the vertices here at least, which is k divided by whatever the conductance is. right? Because there are k edges in that cut, and the conductance is phi, so you have k over phi vertices in that. And in this case, the net conductance of all these things together is like phi divided by epsilon. So as long as phi is sufficiently small, you can get the math to work out. And well, I mean, I'll cut to the punchline, which is the next slide. Actually, we show like you can actually get such a magical k. And this is where spectral methods come to the rescue. So this is a bit wordy. I'll go through it slowly. So let's fix this free set F, which is of size epsilon n. So it's like, assume everything else has been clustered so far. You've got this set of vertices which need to be partitioned. There is a magic bound K. So I wanted to show that this was magical, but because I have two daughters, the only way I can do that is to color it in pink, right? And to me, like pink is magical. So therefore, that's why it's in pink and in squiggly letters. So there's this magical bound K. So that for at least, just think of it as at least some number of vertices comparable to F. They may or may not even lie in F, but you can argue that okay, so I'm lying a bit here, but an adaptation of Spielman-Teng local partitioning will yield a cut, which is the green part, with these two properties. The number of edges that are cut by C is exactly going to be this bound K. And the conductance of the red portion is actually going to be small. What is remarkable, maybe remarkable is a bad word to use when you're talking about your own result, but I still find it remarkable. Okay, so sorry. Is that you're doing diffusions in the original graph. The diffusions actually don't know what this set is. Yet nonetheless, you're able to bound the conductance of the intersection with this unknown set for sufficiently many vertices. And you can also get the number of cut edges to sort of be exactly okay. So there is this bound, so that for some sufficiently large fraction of vertices, the total cut size is going to be K. By cut, I mean the number of edges cut is this magical bound. And the red portion is low conductance. This is like, you put your helmet on, you put all your protective gear on, and then you go into the labyrinth hoping that you will emerge someday. And so you have to really get into sort of the guts of the Spielman-Teng and something called the Lovász-Simonovitz curve technique, which is used. But once you sort of emerge and you come, you see the light of day, you get this parameter K. And so now that you have this parameter K, moreover, this parameter K can be computed locally. It can be computed in polynomial in 1 over epsilon time just by random sampling. Essentially, you just randomly sample in a vertices, you look at what Spielman-Teng does, you can kind of collate all those things. So this part is not hard. Once you prove its existence, to show that you can find it is not hard. So you can imagine that in some sense, this magical K can be computed essentially by all vertices, as long as they have the same randomness. You need oracle access to F though, right? So the bound, so here's what's kind of weird. The diffusions are independent of F, but this number depends on F. So to actually compute what the number is, you do diffusions in the whole graph, but you kind of look at the intersections with F. So you need oracle access to the free set to be able to do this. This is a caveat. If this is confusing, ask me later and I think I can answer. So now let me just update my clustering. Now that this bound K is known, so everybody knows this bound, for every S in order, we're going to do this clustering part. We're going to run local clustering from S to get this set CS. If this exactly cut K edges, like theta of K, then fine. If not, just make it a singleton cluster. And then you output the pieces before. So it's like saying that we know that the right cut has K edges. So we'll only consider cuts that cut K edges. And so what this sort of gives is that the bad cuts, the wrong cuts will be at most K edges. And your right cut will have K edges and cut lots of vertices. So then you can amortize everything out. So I'll just sort of say this again. The amortization works, meaning that all the cuts will have at most K edges because we enforced that, right? We basically said, if it cuts K edges, keep it, otherwise it's singleton. So then the cut will just be constant size. So every cut is exactly K edges. So these red portions will cut at most K edges. In 1 over epsilon iterations, we'll see this one good seed. And that one good seed is exactly what is promised, here. That is that one good seed. So in 1 over epsilon turns, you'll get that one good seed that satisfies these conditions. And then you'll see that one good seed, and that will have a size of k divided by phi, and where the phi was actually really small. So you will get essentially after 1 over epsilon iterations, think of it, you're going to cluster a large set. And even though you cut extra edges in those previous iterations, the conductance of this piece was so small that it was still worth it. And so if you put it all together, the net conductance, so this is maybe something to mention, is that it's not true that every piece in your hyperfinite decomposition has low conductance, but sort of globally, the total number of edges cut is small. So that is what you get out of this. Unfortunately, we're not done yet, because, as I said, this bound k depends on what the free set is. As you're partitioning more and more, you are going to be clustering out various portions of the free set, this red part, and so the free set shrinks. And then that size is not valid any longer. So then you have to recompute it, and you get a new size for that f. And you can prove that only polynomial and 1 over epsilon recomputations are needed. Right? So this is, if this missed you, it's okay. Don't worry about that. But the point is, what you can do is you partition your vertices into phases so that each of those phases uses the same value of k. And then at the end of the phase, you just recompute this k using a local algorithm. So one way I like to think of it is that you have this local algorithm that initially nothing has been clustered. Everything is free. That is what I call t is equal to 0. You're going to compute this number k0, which is like the right cut size you need. And you will go ahead and do this partitioning until at some point after like alpha n iterations, the free set has shrunk somewhat. Now what you do is you kind of have to sample from the situation, and then you can compute a k1. And then with the k1, then you can sort of proceed. You will get a k2, so on and so forth. So you can think of what this local polynomial in 1 over epsilon algorithm doing is that it's actually looking at snapshots of the future and guessing what all these values are. So it's going to compute these values k0, k1, so on and so forth, which are like the right cut bounds for each of the phases. And the way to think of the actual algorithm, how it works, is as follows. Initially, think of as a preprocessing step. We first compute these numbers. So polynomial and 1 over epsilon numbers, these are like these cut bounds for each phase. And then each vertex S in order, based on its phase, it's going to choose one of these values as its cut bound, and then essentially run the procedure with that cut bound. So it's mostly what I said, the algorithm is pretty much the same as what I've been discussing thus far. It's just that for every vertex, you have to find some appropriate cut bound number. And once you discover this number, you can get everything to work. Once you have such a procedure, you can convert it to a local procedure by this anchor finding. So this is the whole shebang, basically. Yeah, I know. We can locally implement everything. The algorithm isn't really that bad. Maybe you disagree, but I don't think it's that bad. But the thing is that everything can be locally implemented. Now, just to answer like the main question in my title, the coordination is done through choosing these parameters. So that cut bounds which were chosen, that's what's doing the coordination. So it's like, think of it as a preprocessing that sets the parameters of the diffusion. And after that, all the diffusions can be coordinated. What is interesting here is that it has nothing to do with minor freeness. And we get these desired global properties of the partition locally by sort of choosing these parameters appropriately. So the magic of spectral graph theory on the toolkit is in helping us find these parameters. Once you get the parameters, the algorithm is really not that complicated. So a lot of the pain is hidden in the analysis. So I have, I guess, about less than 5 minutes left. And so, is that 5 minutes? Okay. So what I wanted to do is actually put out a few challenges, some questions that I have that, Maybe they will inspire you, maybe they won't. But some of them do keep me awake at night, and I'd like more people to be awake on them. The first one, which goes back to Madhu's question on the random seed, and this is maybe something even Reneet may ask, is there a local computation algorithm for partition oracles? So this is equivalent to saying, do you really need a linear amount of randomness, or can you do away with much less? I believe that you only need polylog n bits of randomness, because in some sense, it seems like you don't really need that much independence for all of this to work. Maybe there's like a clever way of doing it using a pseudo-random generator and just arguing that, oh, if you have log n-wise randomness, then all the concentration bounds are going to check out, and that is enough to make it work. Or maybe one has to go more clever and maybe use I'll just say this, one of the thoughts we had was, can you use Nissan's small space pseudo-random generator, convert this into some kind of streaming algorithm that doesn't use much space, and then use a pseudo-random generator for that. So something. I think that this is very much doable. Can we get constant size random seed? I don't know. Some part of me says that that should not be possible, but I don't know how to argue that. So I'm going to put my badge on this challenge, as this is a doable challenge, and it requires some digging into the analysis. Yeah, Seper?
Say constant size and constant boards or constant bits of random?
Bits.
So then you don't even store one vector. You cannot even sample a random vertex.
You can't even sample a random vertex. So the thing is, as it turns out in these things, the only thing that is required is you don't really need a random permutation. It turns out that I think if the phases are random enough, then things will work. But maybe I'm speaking nonsense here. So maybe this is not possible. I should. Yeah. So.
Actually, local algorithm shouldn't follow really many wise independently enough, so that it looks random in the local neighborhood that you're looking at, and then the expectations of the number of cut edges, number of regions.
So there are some places where we're doing some kind of union bound over all vertices for certain calculations, and then there, it seems like polylog n bits random, because when we're doing the amortization argument, we want every so often there should be one good vertex, and in those we seem to be using log n wise randomness.
Use whatever, and then you can just say the expected number of regions and the expected number of cut edges are what they should have been according to that other population.
I'm glad that this is keeping someone else awake as well. So I don't know, off the top of my head, maybe let's take that offline. I'm not sure, but I think there may be some. I don't know. I thought about it a bit, and I thought that it was very hard to get there. I could be mistaken. Okay, so challenge 1. See, I told you it's doable. I told you. Challenge 2. Are there distributed applications of this? It seems like there should be there, right? There has to be some distributed graph algorithms problem to solve. I don't know. Distributed algorithms for property testing on graphs, maybe something for planar graphs, some kind of distributed spectral clustering. Please, those of you who know more about distributed algorithms, please tell me. Doable? Maybe. Can we get a better running time? Right now, the exponent is 3000. We didn't try to optimize it. I think you could bring it down to less than 5 by just doing the math carefully. Can you get it down to epsilon to the -2? Okay, I said doable because I think you can get it down to less than 5. I don't know if you can get the actual linear. That would be really nice. Last but not least, can we handle unbounded degree graphs? This seems really hard because the graphs are not hyperfinite anymore in the true sense, but you can break it up into pieces whose diameter is bounded. Can we have a notion of partition oracles for those? That seems hard. So now that I've ranked all my problems, thank you very much, and hopefully you have enough to think about.
Okay, so thanks, Sesh, for this magical, or was it remarkable talk? Do we have more questions?
Thanks for the interesting talk. So regarding the distributed application, so it seems that the straightforward to use this kind of framework is to compute K0, do some computation, go for K1 and so on. Have you given any thought on the total cost of this, like the sequential time?
Sorry, say that.
So you want to do K0, do some local computation, and then you have to wait for that to be done
Yes.
for all the nodes, and then go to the next phase and next phase. What's the total running time?
That's a great, we haven't thought about that enough. I think that's a good question right now, because in the sampling model, we don't worry about how to communicate things that are far away. And I don't know if there's a good way of doing that, but that exactly, you're right. I mean, if we could figure that out, then we could probably get this distributed clustering to work.
Just out of theoretical interest, have you thought about this magical sequence, whether it's monotonic or it has any other properties?
No, it's a good question. We don't have any properties on it.
Thank you.
So I have some question about the challenge 4 slides. So yes, so the graph you're considering has a bounded average degree, right? And so I wonder what is the bottleneck here to handle unbounded degree graphs?
So think of like a star.
Yes.
So in a star, like there is no hyperfinite partition. The whole thing is just one piece. So you cannot afford to actually output the whole piece as a go. So one needs to redefine what it really means to have a partition oracle. I think that it's like every vertex, when you call it, will output some label. That is the label of the cluster it belongs to, such that all the vertices that have the same label have some nice property, and at most epsilon fraction of the edges go across those clusters. But we don't really know exactly what is the right property those clusters should have. But we have some ideas based on graph minor theory.
I see. Thank you.
Okay, more questions? Okay, let's thank Sesh again.